I'm going to start with some warm-up questions that will help you hopefully understand the nephron, especially since we're getting to the nephron loop or loop of Henle. Yeah, you gotta understand osmosis to understand that. So we're going to start off with this. So let's start off with a throwback to osmosis. Again, this was from last semester, but it's a critical concept in understanding the nephron. Now, let's start this question here. Alright, so you have two solutions basically here, just like solution A, solution B. One has 100 mg per deciliter glucose, the other has 200 mg per deciliter glucose. So if you just have this semi-permeable membrane that separates the two, that allows water through, but doesn't allow glucose through, what will happen? Which way will the water flow, if at all? And if you're watching the replay at home, just pause the video and try to answer it before I reveal the answer. Well, over time, what will happen is this. It will gain water in like solution B. Why? Because it has more glucose, and glucose and water attract each other, but glucose can't move. So what's going to happen is that the higher concentration of glucose is going to draw more water to balance out the concentrations of the two solutions. Next question, and here we have two solutions, but solution A has 75 milliequivalents per liter sodium ions. Solution B has 150 milliequivalents per liter sodium ions, and just pretend that it's just sodium ions, nothing else in it. So which way will the solutions move? Will move towards solution A or solution B. So over time, one of these will experience a change because we don't have equal concentrations of solutes. The most popular answer was solution B will gain water, and that is the correct answer again. Why? Because sodium ions attract water and vice versa. So this is what the higher concentration, so it's like thinking of a tug of war. Which side is going to win out? The part with more people on one end or the part with less people on the, or fewer people on the other end? Well, the part with more people pulling is going to win out. So that's why solution B will draw more water to it over time, even if you start off with the same volume of these two solutions. Next question. Okay, so now we have another two solutions. So here we have a semi-permeable membrane that only allows water through. Here we have two solutions. One is pure water with no solutes. The other is sodium chloride at 154 millimolars. So sodium chloride dissolved into sodium ion chloride ions. So which side, what will happen to water over time? Okay, let's look at the solution, and it seems like the majority of you now said solution B will gain water, and that is correct. Because why? Pure water is going to be basically 0 millimolars sodium chloride. Now, I won't ask you to convert between different concentrations, but again, you don't have any solutes here, so basically you just have solutes here that are trying to pull water toward its side. So that's why solution B will gain water over time. And this is a critical concept in understanding the nephron. Alright, so let's talk about the urinary system. So we left on the proximal convoluted tubule. Now let's talk about the nephron loop. So there's something called a descending limb. So this is going to go deeper into the medulla, and then it's going to do a UE and this little turn here and go from descending to ascending. And then what we see here is that what we have is a concentration over here. So we have this concentration in units of milliosmoles per liter. So basically it's like the concentration of solutes that can do osmosis or contribute to osmosis. And that's why we covered osmosis earlier. Okay, so then what we see is that as you dive deeper into the renal medulla, is that we see this concentration inside the renal tubule and this part of the tubule called the nephron loop or loop of Henle. We see it getting more and more concentrated. So it's not just sodium and chloride. There's many other things like potassium, calcium, glucose, if there's any spillover, or urea. So all the solutes in there, that's the rough, that's a measure of the concentrations of solutes that can draw water. So as we see, what we have here is that as we get closer and closer to the medulla, this gets more and more concentrated. So that's why this number increases and increases and increases. So more solutes means more pulling water out of that solution. So that as you go from 900 to 1200, you start pulling out water. Now, why does the concentration inside the renal tubule also change? Well, it's kind of like leaving a soup on the stove and letting the water boil off. As you have the water being removed from that soup, you notice it gets more and more concentrated. Or it's like leaving a drink or something that's water based out in the sun. Eventually, like all the water will evaporate, and then you'll have a more concentrated residue or solution left over. So that's what we have with this. As you start to draw out water from the renal tubular fluid, you start to concentrate it more. But as you go back up, then you notice that it's starting to decrease in concentration. So this is kind of like another way of looking at this. So what happens is, like, due to that increase in osmolarity and the amount of solutes that draw water, as you go deeper into the medulla, you start to draw out more water from the renal tubular fluid. But when you go ascending, it's very interesting. And actually, to backtrack a bit, so the descending limb, it's also thinner. Like the walls of this tubule are thinner compared to the ascending limb. So the thin walls allow water to diffuse and do osmosis, or like it's a thinner membrane. So water has an easier time passing through a thinner wall than it does have a thicker wall. Now, when you get to the ascending limb, and this is why it says like impermeable to solutes in the descending, but as you go back up, now water is blocked. So this membrane is no longer permeable to water. So water cannot move out of this part. But the interesting thing is that you have these things called transporters. And actually, this is where Martini is a little inaccurate. Sodium chloride, yeah, I expect you to know that part, but it also pumps out potassium as well. So it uses ATP and energy to move this sodium and chloride out from the renal fluid and out of the renal tubule and into the medulla. So the thing about this is that what's the overall effect? As you pump sodium chloride back into the interstitium or basically the fluid surrounding the tissues of the renal medulla, this part gets saltier. So the more you pump out here, the more salt and solutes you have out on the outside. So this is why you have this high concentration of solutes right here, because you're pumping this out as well. Now, the cool thing is it kind of builds on each other. As you pump out more sodium chloride, you draw out more water via osmosis. And as you draw out more water, you have more concentration of sodium chloride and other electrolytes. And then you can pump that back out, drawing out more water, concentrating more ions, pumping out more ions. So this is a process we call countercurrent multiplication. And why is that? Well, this current goes this way, this current goes the other way. So that's the countercurrent part. But the multiplication part is because you're drawing out water, concentrating ions, pumping out ions that draw out more water, and the whole thing builds upon itself. So it's kind of like a positive feedback loop where you have an amplifying, because again, the drawing out of water helps to concentrate more ions, the pumping out ions helps to draw out more water. So they're both helping each other along. Now, when we look at it here, so this is why the renal medulla, I like to say it's very salty, because you have all these electrolytes, and not just electrolytes, you also have other ions such as urea. So yes, urea is a waste product, but it also helps with osmosis as well. So you have a very high concentration of all these salts and electrolytes here. So that's why the renal medulla helps to really draw out water from the fluid inside the renal tubules. So this is what's interesting about the nephron. So where does all those ions and where does that water go? Remember that we have these blood vessels that surround the renal tubule. So again, the renal tubule isn't naked by itself, and the efferent arteriole doesn't just go back to the systemic circulation in your body. What happens is that if you draw out water, and if you draw out sodium and chloride and all the other electrolytes, it ends up in the interstitial fluid between the tubule and the blood vessels, but this can also diffuse and end up in the blood vessels itself. So that's the key thing with the nephron, is that you're always trading things between the blood and the renal tubule when you have the flow of fluid and plasma in the nephron and the capillaries that surround the nephron. Okay, yeah, so vascularity. So this is what this is showing you in the Martini version. I like this broken. I know it's kind of hard to see in this version, but what you see is that, okay, we have this renal tubule and over here, and as you descend into the medulla, you start to draw out water, and that water ends up back in your bloodstream. So actually it's interesting because your bloodstream, when it's in the medulla, these little capillaries, they do get very high in concentration, but as you're drawing out water from the nephron loop, that helps to dilute it so it's back to normal osmolarity. So normal osmolarity is around, well, for the purposes of this class, let's say it's around 300. It's actually a little less than that, but don't worry about that unless you're going to like medicine or nursing. All right, so then what we have here is like when you're going ascending, this is where we're starting to pump out. And again, if you draw out water, you're going to concentrate those ions. Those concentrated ions are going to be pumped out via these active transporters that you burn up ATP, because why? You already have a lot of electrolytes out here, so it's hard to, just by nature alone and without any additional energy and passive transport, to move electrolytes from inside the tubule to an already high concentration. So that's why you need to add ATP, and this is why you have that increase in this concentration. Now what happens over time is that this is why the tubular fluid decreases in osmolarity as you get back up to the distal convoluted tubule. And then we're going to talk about that later on and very, very soon. Okay, so the nephron loop of Henle, what is the main thing? So we went from the proximal convoluted tubule and now we're here at the nephron loop. So again, this is a thin descending limb. So this thin part, through osmosis, and because the renal medulla is very salty and has a lot of solutes, it's going to draw water at first when it's descending down into the medulla. Now the other thing is like, okay, so it's going to reabsorb water, and it's also going to like, and electrolytes as well, but the electrolytes are in the other end. So the part that goes back up and out of the medulla, that's the ascending limb. It's thick, so it's impermeable to water at this point. But you're going to pump out all these electrolytes like sodium, chloride, and potassium into the renal medulla. And it also secretes urea, but temporarily, and I'll cover why it's temporarily shortly. Okay, so the nephron loop, the main thing is water and salt and electrolytes, especially sodium, chloride, and potassium. So the main purpose of the nephron loop is to reclaim water, reclaim electrolytes, and put it back in your bloodstream. So that's why, and the thing is that as you draw out more electrolytes, you draw out more water. As you draw out more water, you concentrate more electrolytes. That's countercurrent multiplication. So the nephron loop is very important in reclaiming water and electrolytes. Now, this is learning golden key points. So that's the main thing I want you to get for the nephron loop. Is very important in that concentration and reclaiming and reabsorbing. Now the next part is the distal convoluted tubule. So distal convoluted tubule, and then it leads to a collecting system. So the distal convoluted tubule, relatively simple, but I don't expect you to know this one right here and the exact ratio of all these exchange right here. But what I want you to know from distal convoluted tubule is that you also reclaim a lot of these ions as well. So things like, and if compared to the proximal convoluted tubule, yeah, they're both convoluted, they both twisty and turny. But the thing is that they have very few microvilli, and that's kind of like a clue to what the distal convoluted tubule is. You already reabsorbed most of your nutrients right here at the proximal convoluted tubule, but you pretty much reabsorbed what you want. Now the distal convoluted tubule, that's near almost at the end, is more about fine-tuning and adjusting the composition of your blood and your urine. So it's going to you can reabsorb water depending on the hormones and other factors in play. It also reabsorbs electrolytes and bicarbonate. So remember that bicarbonate buffer system. So bicarbonate is a weak base. So if you're reabsorbing bicarbonate from the renal tubule and back into your bloodstream, you're adding base and alkaline to your blood. So this is going to make your blood pH be more alkaline and increase the pH of your blood. And certain xenobiotics, I don't know if I got to cover this term in depth, but basically these are chemical compounds and molecules that are foreign to your body. So some drugs can be also reabsorbed at this part right here, but I think it's more if you're going to like nursing or medicine, you'll have to know that when you take your pharmacology classes. Now what it's going to do is also secrete, so it can secrete things like protons. And remember that the concentration of protons, aka hydrogen ions, that determines acidity. So if you're secreting protons, what are you doing? You're taking protons from your blood and interstitial fluid surrounding the tubule and dumping it in the fluid that eventually becomes urine. So what we have here, you're reabsorbing base and you're secreting acid. So this is a very important part of the kidney, is that it's able to maintain pH by If you want to make your blood more alkaline, what are you going to do? You're going to reabsorb more bicarbonate over here, and you're going to dump out more acid. Because why? Because acid is going acidic, right? So protons are acidic. But say you're having your blood, the pH is too alkaline. What can your kidneys do? Reabsorb less bicarbonate and secrete less protons. So this is one type way your tubules are able to, and your nephrons are able to fine tune the chemistry of your blood. Also potassium as well, and ammonium. So remember that, like especially in transamination and deamination of amino acids, when you burn them for energy, ammonium is a major byproduct, and so is urea. So you can secrete excess ammonium into, like if you build up ammonium in your body, it's actually a toxicant that's harmful to your cells. So if you have a buildup of that, it's important to dump that. So again, reabsorption is kind of like, because urine eventually leaves your body, right? So it's kind of like, if you ever seen like those waste or refuse processing plants, sometimes they reclaim and recycle things that are valuable, but the stuff that sometimes you might dump extra stuff that's totally waste you don't need. So reabsorption is like recycling, secretion is like dumping. Now, when you get here to the collecting ducts, misspelled. Okay, so collecting ducts is going to secrete protons, and so you have more secretion of protons and potassium, but you can reabsorb sodium chloride. And again, why? Because again, if you've lost osmolarity to your blood will also lose its ability to retain water. So you're reclaiming more of the stuff that helps to keep your blood volume and your blood pressure as well. And you're going to reabsorb water, because otherwise you'd be losing a ton of water if you didn't reclaim it throughout your nephron. And also you're going to, so this is an interesting thing about urea. You might be like, oh, urea is a waste byproduct. So you kind of have this recycling. You kind of reabsorb it in the nephron loop, but you also to an extent in the proximal convoluted tubule, but you're also you're also reabsorbing it. So you're both secreting and reabsorbing it. So the renal medulla is actually full of urea. It has a high concentration because urea helps with osmosis. All right, so now we're in the distal convoluted tubule, and now we're going to end up at a collecting duct. So what we have here is here's the collecting duct, and all these solutes and any fluid that's left over, that eventually becomes urine. But the collecting duct itself can also do some fine-tuning itself by its own form of fine-tuning. So here we have water being reabsorbed in the collecting duct, and again, the collecting ducts do travel through the renal medulla, so that very salty renal medulla is going to draw out more water. So this is what we have here. And when you have something that might sound familiar, called antidiuretic hormone, that is going to increase the amount of these protein channels that are called aquaporins. And these aquaporins, aqua sounds like water, right? And porin sounds like pore. So it's these little channels that allow water through. So it kind of increases it. It's like adding more lanes to a highway, or adding more, or doors, opening up more doors. So this allows, aquaporins only allow water through. So by allowing more water to flow between the renal tubule and the interstitium of the kidney and the renal medulla, you're going to have more waters drawn out via osmosis through that very, very salty renal medulla. So that's the overall effect of ADH, is it opens up more channels for water to go through. So it kind of speeds up the flow of water from the tubule to the renal medulla. All right, so ADH, so what's going to happen is that this is why you produce what we have is like a small volume of concentrated urine. And why is that? Well, you drew out a lot of water and put it back into your bloodstream. So more water in your bloodstream means less water in your urine. And as you're drawing out water, what are you doing? It's kind of like that boiling pot. As you draw out water, you make it more concentrated. So this is why ADH, if you add that to the equation, if you increase your secretion of ADH, you're going to have less volume of water in your urine, and you're going to have very concentrated color to your urine as well. Because why? Well, there's a pigment called urobilin, also known as urochrome, like color. So what's going to happen is that if you decrease the volume of water, you're going to increase the concentration of this urochrome, or aka urobilin. So this is why when you have ADH, you have a darker color to your urine. So that's why if you're dehydrated, well, if you're dehydrated, what do you want to do? Do you want to get rid of more water, or do you want to retain and keep the water you do have? So this is why antidiuretic hormone is going to decrease the volume of water so that it stays in your blood and you don't lose blood volume and pressure by urinating out a large volume of fluid. And why do I make such a big deal about these transporters? And actually, if you're going to med school and nursing school, you have to know this too, is that these transporters are very important because they're found all throughout the nephron, and different drugs that are called diuretics. The overall purpose of diuretics, like caffeine, that increases your volume and urge to go and urinate, right? So diuretics are going to they're going to prevent the reabsorption of water from your tubular fluid and urine. So this is what one type of diuretic does. It actually blocks those aquaporins. But a lot of those diuretics, they actually block these transporters that move solutes from your renal tubular fluid and reclaim it and reabsorb it. And they might be like, why does it do that? Remember, where does the water go? It goes toward the side that has more solute concentration. So if you're blocking these transporters that put solutes back from the renal tubule and back into your body, these solutes are going to stay in your renal tubules. And if these solutes stay inside the tubular fluid, the water is going to go along with it. So the insides of these renal tubules and nephrons are going to get more salty. It's going to draw more water. And this is why you have if you have increased water in these renal tubules, that's why you have more water with that's why these are diuretics, because you have more water inside the renal tubules, therefore leading to an increased volume of water. So that's why it's important to know the nephron. Yes, it does seem complicated. I just covered the surface of this, but if you're going to anything that's healthcare related, you have to know this, especially pharmacology, nursing, medicine. You gotta know that. But again, just keep it to the basics for now. So what the big thing about the distal convoluted tubule and duct collecting duct, they're kind of like the fine tuning. They're going to fine tune pH, they're going to fine tune urine volume, and also and solute concentration as well. And another analogy I like to use is to this. Okay, so here's a toilet, and say you drop your valuables in the toilet. What are you going to do? Are you going to just let your valuables go and then use the restroom and then dump the waste in there? No, what you're going to do is take your valuables out first. So if you have your valuables, you want to fish them out. And then when you fish them out, then you want to dump all the waste in that toilet, right? So again, this is kind of like a rough analogy with the nephron. In the very beginning, you reclaim everything you want it to keep in your body. But at the very end, you start dumping out all the waste that you don't want in your body. And that eventually becomes urine. Okay, learning goals and key points. Again, this is in the slides, but yeah, and there's more that the DCT and collecting tubules, collecting ducts do. But for this class, keep it limited to what I covered.